talk more about the exam on Monday, but just to give you some very basic information. So it's a 50-minute class, obviously. What I'm going to do is I'm going to write the exam to be approximately 40 minutes for the quote-unquote average student. I have this process that I use that gives me an idea of how long most people should take on it. That doesn't mean that everyone will finish in 40 minutes. Some people will probably finish early. Some people will probably need the full 50 minutes. And then what I'm going to do is I'm actually going to make the time limit 60 minutes. So what I'm also going to do in case you have a class directly after this or something like that is I'm also going to open it maybe 20 minutes early. So it'll open around 11:40 instead of 12 in case you want to take it a little early. Now that time limit is official. It's not like the quizzes where you can keep going. It's once the 60 minutes are up, what you finished is finished and what you haven't, sorry. So they will auto submit after that 60-minute time limit. It hopefully will not take any of you 60 minutes because it's going to be written to be a 40-minute exam. But that is what it is. Let me reshare my screen in case people can't see it. You don't need to be on Teams, but if you want to, or you just need to ask questions at any time during the exam, I will be here. So I'll be here, you know, just twiddling my thumbs or something on Teams. And if you need to pop in and ask a question, or if you just want to, you know, sit here the entire time just in case, so you don't have to like pop in and pop back out each time you have a question or something like that. I haven't written the test yet, so I don't know how many questions there are going to be. I will be able to tell you more about that on Monday. It will be through Blackboard, just like the quizzes, though. So we will talk about more of the specifics about it on Monday, the setup, question types you'll see, and all of that jazz. We'll talk about that a bit more on Monday. I want to make sure we can get through all the notes we need to get through today. So on Monday, we'll talk about more about the specifics. And I also have to write it. The only other thing I want to say is that there will be a review up tonight. I don't know exactly when today, but later in the day, the review will be going up. It will have the list of topics that the exam will cover and also some practice problems. The answers won't be up right away because I'll need to write them, but once I have them written, they should be up by the end of the weekend, definitely, probably on Saturday. So those will be up. That is the thing that I suggest studying first because I write your exams and I write the review. So, you know, the homework questions and that kind of thing are good practice by all means and are good study aids. But if you're like short on time and you've only got a time to study, you know, one specific thing, one specific method, and either you can study the homework or you can study the review, So I'll talk about that a bit more on Monday, but that's going to be coming your way tonight, and you'll have the answers by the end of the weekend. Your homework. We should be getting through a decent amount of notes today, so you should be able to do the large majority of it, but I was too optimistic with what we were going to cover this week. I very much try not to do that, but this week got away from me. So there's some that you can't do. So what I'm going to do is I'm going to change the official due date to the 15th, not this Monday, but next Monday. I would highly suggest still doing, and I'll try to, at the end of class, I'll try to tell you which ones you can do and which ones you quote unquote can't do yet. I would highly suggest still completing the ones that you can do by Monday so that you get that practice for the exam. But technically the due date would be the 15th because that will allow us to finish the notes that we need on Friday after the exam so that you can actually finish that homework because I was a bit too optimistic. So that's the thing. I will be sending information about that on Blackboard just so that's official in case anyone missed it or isn't here or anything like that. So that'll also be coming out in a Blackboard announcement later today about the homework. Anyway, we'll talk about the exam in much more detail on Monday. I want to finish these notes, so let's go ahead and pop over to our notes now. So we're talking about exponential functions, remember? So that's our functions that are taking the form p naught a to the t with our rate as r and taking the consideration of 1 plus r. We've got exponential growth, exponential decay. And remember, we've got a difference between a factor being the a value and the rate being the r value. So what we're going to need to do now is we need to figure out how to actually find an equation of an exponential function if we're just given 2 points. So what we've done so far is we've done finding the equations if we're given the initial value and the rate, but we haven't looked at, well, what if we're not giving any of that? We're just given 2 points, just like, you know, I can ask you to find the linear equation between 2 points. So if we want to find the equation of an exponential function given 2 points, you can always use the following process. In certain problems, they can be solved slightly faster, and I'll show you that on one of the examples in a second. But this process as written always works. So you don't necessarily always have to use it, but there are cases where, you can speed it up a little bit, but then there are cases where there's no other choice but to do this full process. So the process is you're going to take both points and you're going to write them in the form P equals P naught a to the t. You know, our generic exponential function notation. You're going to divide the two equations, and you're going to see why that's helpful in a second. Now, my suggestion is to put the equation with the larger t value on top so that your algebra is easier. So essentially, if you flip-flop them, you can still solve it by all means, but there's a lot of extra algebra, and like halfway through the extra algebra, you just get out to the exact same spot you would have gotten if you just put the larger value on top. And I'll point that out when we get there. So what that allows us to do is that's going to allow us to, goodness, why is it doing that? It's going to allow us to solve for A. I don't like that. A. And then essentially once you have that A value, you can use it in either one of the two functions that you originally wrote down to be able to solve for P naught. It's a kind of long, kind of tedious process if you have to do the full thing, but sometimes you have to. So I'll leave that up for, oh, wait, what was, I did note this for the other class. This is the step you can sometimes skip. And it's almost like being able to skip the P naught step actually makes this step 2 a lot easier as well. And again, I'll point out the difference when we get to one of those questions that can do that. But if it's going to be harder for you to, you know, remember 2 different ways, then just remember this way, because this way always works, no matter what. So leave that up for like 5 more seconds in case anyone's still writing that down. We'll do a couple examples. All right. So I'm going to zoom out a little bit. And if you write very large like I do, prepare yourself because you might need to write a little smaller. So let me break this up so I don't run out of space. So what we want to do with these is we want to write the equation for the exponential function for the graphs that are shown. So essentially the points are set up, everything that's on the axes, the little notes are specifically for those points. So essentially in this first one, we have 0, 100, and we have 3, 21.6. Now this is one of them that we could do the shortcut way on, but I'm not going to. I'm going to do the full way on this one anyway. I'm going to do the shortcut way on the second one. So on this one, we're going to do the full way. And actually, since I'm doing the shortcut, I don't need as much space. So let me get myself more space on this one. So if we're going to do the full process here, what we're going to do is we're going to take both of those points and plug them into our generic format. Now, for the ease of the algebra, we want to write the one with the larger x value on top of the other one. So what we're going to do is we're going to write 21.6 equals P naught a cubed. 100 equals P naught a to the 0. And we're going to write them one on top of the other because it's just going to make the next step easier to visualize. Technically, it's not necessary if you just keep track of what you're doing, but it's easier to visualize what's happening if you write them one on top of the other. Because what you do next, actually, let me split this up even more so I don't run out of space. What you're going to do now is you're going to divide both of these equations. So 21.6 divided by 100 will give you 0.216. Now the point of doing this, because once you do that, notice that we have P naught divided by P naught, which just cancel each other out. So we no longer have any P naught, which is good because we can't have 2 variables. don't know how to solve for two variables at once. And then algebra reminder, when you divide things that have exponents, you're going to subtract their exponents. So we're just going to get a cubed here. That 2 is a little. And then to solve for a, we would just have to cube root the other side, which will get us that the a value is 0.6. Questions on how I found that? So just to be clear, and because someone in my other class asked, so just in case someone was trying it here, if you were to flip-flop those over and you divided them, 100 divided by, come on calculator, 21.6. The p naughts would still cancel out, but then you would get a -3 as your, oh my goodness, I'm throwing things, as your exponent on the a value. And what would technically happen then is a negative exponent is equivalent to a positive exponent in the denominator. So then you'd have to multiply both sides by a cubed and then divide both sides by the 4.6296, which would give you this. And again, I kind of already mentioned this, but we did all that extra algebra to just get out to the same exact step over there. So technically you can solve it that way. It's just a lot more algebra that you need to keep track of, and I personally just try to be careful and put the one with the larger t value on top so that I don't have to do that. So I'll keep that over there for a couple seconds in case someone wants to note it down, but yeah. So we're not done this question because we found the a value, but we don't know what, well, I'm pretending we don't know what p naught is. We know what p naught is. Oh, clarify that as well. Where do I want to write that? I'll write that over here because I think it's like implied, but I've never officially stated it in this format. P naught is the initial value, right? Now that phrasing might be misleading because you might think, well, the initial value is all the way back here, right? The initial value is when t or x or whatever variable you're looking at is 0. It's essentially the y-intercept of the function is what p naught actually is. So that's why I know technically in that first problem that 100 should be my p naught value. I'm going to go about the problem as if I don't know that, but in the second one we'll see how we can just use that to make the problem easier. But if we don't know that, what we would do now is we would pick whichever one of these two equations makes us happier. I'm going to pick the a cubed one because the other one's going to be very not helpful. And you're going to plug in the a value you just found. So there are some questions where you have to do this process, so that's why I wanted to do it. So we'd get, whoops. Come on, erase. 0.216 when we cube the 0.6. Divide both sides by the 0.216, you'll get that p naught is 100, which is what we imagined it was, which we would, oh my gosh, which is what we knew it should have been anyway. And now we can write our final equation, p naught a, and technically this is in terms of x, so it would be a to the x here. Questions, concerns on that? Now the only thing, I don't know if it's an issue on WebWork because I don't think you're ever doing one of these where you're given p naught. So it wouldn't be a problem. But I'm going to say it anyway. Now it didn't happen in this specific question because the numbers came out to be super duper nice. But I've seen a question before in my life on my old set of notes that I trashed that question, where if you do this full process, say you were given the graph and the p naught was 100, and you do the full process and the p naught you get out is like 99.6. And that would happen because of rounding errors along the way. Like once you round a number, it's going to change the final answer. So be very careful if you're doing the full process on these, if you technically are given P naught. If you're technically given P naught, that's the value they're going to expect for P naught. So say we were given 100 here, but then for some reason our math came out to 99.6 and you used 99.6. I would probably accept it on a quiz or an exam because I would know where it came from, but WebWork would probably tell you you're wrong. So just be careful of that. Anyway, again, I still wanted you to see the full process because sometimes you need to use it. There's no choice. So let's look at problem 2 here after I erase this a little bit over here. So problem 2, what are the points we're given? We're given 0, 32, and we're given 2, 92.5. So let's do the shorter way on this one. So we are given P naught because the initial value, the y-intercept of this equation is at 32. So that's our P naught. So if you have P naught, the kind of shortcut you can take is you still put the other point into that format, but you just plug in P naught. So in the other one, we left P naught as P naught. And here, because we know P naught, we're going to plug it in. And then we're not going to write the other equation. We don't need it. Because at this point, what we can do is we can divide both sides by 32. Get 2.89 approximately. And if you were to do the long process, essentially the long process, this step, this step here would essentially link up to this step we had over here. So it saves you a little bit of time, not like a ton, but a little bit of time. And then of course you don't have to find P naught afterwards. So we would have to square root this to get that A is approximately 1.7. So since we have A and we don't need to solve for P naught this time because we're just given P naught, we can just, so actually let me box these answers so it's easy to see where they are. So our final equation would be 32 times 1.7 to the x, because again, this question is given in terms of x. Questions, concerns about how I found that? Okay. The last one, we have points -2, 9.5, and 1, 0.5. This one we can't shortcut at all. We have to do the long process because we don't know what this value is. We don't know P naught. So we need to write both equations in our general format. I suggest putting the one with the larger t or x value first on top. So I'm going to write the 0.5 equals P naught a to the first. And then the 9.5 P naught a to the negative second. Actually, I did a dotted line over there. Let me be consistent. So if we divide these two equations, let's divide them. 0.5 divided by 9.5 is, I'm going to take 4 decimal places today because that's what I feel like taking today. So 0.5 divided by 9.5 would be approximately 0.0526. We'd have a to the 1 minus -2, so we'd get +3. And we would need to cube root that. Also, in terms of typing that into your calculator, because you can do a cube root, it's grosser to find than just doing this. I personally like to just do a fractional exponent. So that will give us, I'm going to take 4 decimal places again because that's the amount of decimal places I'm feeling today. So we get our A value is approximately 0.3747. Here, since we don't know P naught, this is when we have to find it. So we take whichever one of these two equations makes us happier. I'm going to do the a to the first one because I don't want to deal with negative exponents. It doesn't matter which one you take. You will get the same answer. Whoops. Or the point is you should get the same answer. It might differ by just the slightest decimal place because rounding, but it should be very, very close to the same number. So we're going to divide both sides by the 0.3747 because anything to the first power is just itself, getting us that P naught is approximately 1.3344. Let me put the full answer down here. So our full answer will be the P naught came out to be 1.3344. A value was 0.3747, and technically this one actually doesn't list the variable, but I'm going to assume it's X again. I don't know why that one is missing the horizontal value, but it is. Questions, concerns on any of that or that process, or I know it's a little long and tedious if you can't take the shortcut way, but it's what works. There's probably a couple other ways you could do it too, but. Okay, I'll leave this up for a couple more seconds in case people are still getting it down. And actually I've got to go grab something real quick, so. All right. So we've got two last questions in this section, and then we're going to move over to the next one. I'll say that in a minute. So suppose a city has a population of 400,000 at time t equals 0, where t is the number of years since 1990. If the city's population decreases by 2,500 people per year, find formula for P of t, the city's population t years after 1990. So decreases people per year. And it's a set amount of people. That amount of people is not going to change every year. Since it's a set amount of people and that amount is not changing, this tells you that this is a linear relationship. And decreases tells you that your slope is going to be negative, less than 0. So if we need a linear function here, we need a y equals mx plus b, or a p of t equals, p of t equals mt plus b in this case. We need our slope and our y-intercept. Y-intercept is when t is going to be 0, which we're given to be our 400,000, and the m is going to come from that decrease of 2,500 people. So our equation here would be, I like to put the positive value first if I have one. It's just personal preference. Of course, you can put the slope first if you prefer. So either of those two equations is perfectly acceptable for that. Part B, if the city's population decreases by 6% per year, find a formula for P of t, the city's population. So we're still decreasing. 6%. So since it's a percent, so that value is actually going to be changing every year because it's going to first be 6% of 400,000 and then 6% of whatever the next year's population was, and then 6% of whatever the next year after that population was. And since the population is going to keep changing, the 6% amount is going to keep changing. So this is no longer linear. That percent is what tips you off to exponential. Now decreases, we haven't actually had one like this yet. Decreasing. All of the ones we've looked at so far have been increasing. So what decreasing is going to do is it's going to make our R value negative less than 0. Now remember, A equals 1 plus R. That's not changing. But here we're going to have that R. The decimal is going to be 0.06 because it comes from the 6%. But since it's decreasing, it's going to be negative. So the 1 plus R is going to be essentially become 1 minus 0.06, which it gets us 0.94. So our equation is still P naught a to the t, so our P naught is still that 400,400. Our A value is 0.94, and it's to the t. So remember, with exponential decay, it means that the R value is negative. So since this was decreasing, it's decay, so it's negative. But the A value just ends up being less than 1. So remember, we never have a negative A value in this class. So if you're given an option of finding the equation, you need to figure out if it's linear or exponential based off of the wording. If it's a set amount per year, it's going to be linear. If it's going to be a percentage or a rate or a factor even, it's going to be the exponential. One other thing I want to say really quick, because I do think it appears on your homework, all of the questions we've gone over here gave us the rate. If they give you the factor, so say we have a population increases by a factor of 1.3. If it increases by a factor of 1.3, that is just your A value. You don't do anything to it. So you have to be really careful about the wording. Do they give you the rate, the percent, or do they give you the factor, which would be the A value? So the only thing left on here are the extra questions, which of course I will put the answers to up on Blackboard if you want to try to look over those for some extra practice. Questions, concerns on this before we move over to our next set of notes? Okay. I'm going to erase this factor pot on the right just to make sure people don't get confused when they just look at the completed notes later. Now we're going to move on to something called the natural logarithm, and depending on how far we get today, I will say something towards the end of class about it. So the warm-up for this section is exponential functions. So actually, I want you to try those two. I'm going to give you 3 minutes to try to set up the equations for those two. Well, actually, the second one you have to actually find a value, so I'll give you 4 minutes to try those, and then we'll talk about them before getting into these notes. I'll give you like 15 more seconds. These ones shouldn't take too long. All right, so the first one, I'm going to just say P for population. If you use a different variable, it's fine because they didn't specify. Initial value is 110. Increasing grows 7% per minute would give you an A value of 1.07 because they give you the rate into the T. And then depositing 2,500 at 3% would give you this equation generically. But then we want to find the amount of money they have after 10 years. So approximately 3,359 and 79 cents. Questions, concerns on either of those? Cool. So the natural logarithm of x, which is written as ln, that's an L, not a capital I. ln of x is the power of e, so remember e is a number, needed to get x. So what that means is if we have the natural log of x being equal to some c value, what that's equivalently going to mean is that e to the c is equal to x. So it's the power of e needed to get x. The natural logarithm can sometimes also be written as log with a little e and then x. And note that the natural log is not defined for 0 or negative numbers. So if like on your calculator you try to plug in natural log of 0 or natural log of -2, it'll give you an error message because those don't exist. Now, in this class, we only talk about the natural logarithm. There are tons of other log bases, log base 10, log base 3, log base 5, log base whatever base you need. You can take any log base necessary. If you know how to work with logs of other bases and you prefer to use them to solve some of the equations we might not get to today, but we'll get to eventually. If you know how to use other log bases, you can use them. But everything that we need to do in this class, even if it could be solved the tiniest bit better with another log, we're going to just use natural log. Because it really doesn't make it that much more difficult. Not even difficult, it's just the algebra gets a bit longer. Anyway, so complete the following statement. So we're essentially going to use that definition to do these. So if y equals the natural log of 10, that's not 10, that's 100. If y equals the natural log of 100, then what to the y equals 100? Well, since the natural log is the power of e to get 100, it's e to the y equals 100. If the natural log of 5.5, that's going to be the power of what that gives what. So the natural log is always the power of e that gives whatever in the natural log. So this would be the power of e that gets us 5.5. The natural log of what is the power of what that gives 500. So these are all the power of e. So if it's the power of e that gives 500, then the thing inside the log must have been 500. These questions are just trying to make us really hit home that definition there. And so if generically e to the m equals n, that would mean that the natural log of n has to be equal to m. So while we won't do a ton of this kind of rewriting, it's one of the main uses of the natural log, really, is to be able to rewrite and go between these forms to be able to solve different things. So say we want to rewrite the following using exponents instead of logs. So we want to rewrite them in terms of their e definition instead of the log. So if we have the natural log of 5, that's going to be the power of e to get 5. So what this is saying is it's saying that the power of e, if I want to be equal to 5, I need to take it to the 1.609 power. Approximately, if you typed that into your calculator. Let me see what it actually gives us. E to the 1.609 technically gives you 4.9978. So that's why the approximation symbol is there, but now the natural log of 1 is actually one that you might actually want to remember in your brain. The natural log of 1 being 0 can just save you a couple seconds if you don't have to type that into your calculator. But this means that we have e to the 0th power is 1, which is a good algebra reminder if you don't remember or you never knew. Anything to the 0th power is 1. I don't care what that thing is, so it does include e to the 0th is 1, anything to the 0th power is 1. But also the natural log of 1 being 0 is also a good thing to put in your brain if you have the space. And then generically, the natural log of a being equal to b would give us that e to the b is going to be equal to whatever a is. So now what if we do, I wish I could fit them both in there, so let me leave that up for 5 more seconds. What if we do the other way? Rewrite the following using logs instead of exponents. So we have e to the 15th equals that really long number over there. So if the natural log is the, power of e to get that number needs to be inside of the natural log. It's a really long number. And that natural log of that number gives us the power. So in part B, we'd have the natural log of h being equal to t, because it gives us the power of the e as the answer. Questions on that so far? Again, we're not going to be focusing on that fact, too much more, but it is important to kind of understand the relationship between the two. All right. What we have now is we have some properties of logarithms, but they're all going to, so these again hold for absolutely any logarithm if you know how to work with other logarithms, but we're just going to use them in terms of natural log. So if you have the natural log of some a times b, notice that the multiplication is inside of the natural log. This does not say natural log of a times natural log of b. It just says natural log of a times b. It's a very important difference. So if you have multiplication inside of a natural log or any log, what you can do is you can split up the log using using addition. So essentially you take that multiplication that's inside and you turn it into an addition of logarithms. If you have the natural log of a divided by b, note, it does not say natural log of a divided by natural log of b. This is the natural log of some ratio inside of the logarithm. Can you tell what a lot of people make mistakes on? Got to make sure the multiplication and division are inside the natural log, and this one you essentially break it up into 2 logs with subtraction. This relates to exponent rules. So, if you multiply 2 things together with exponents, you add their exponents. And like we just saw, if you divide 2 things with exponents, you subtract them. That's kind of where these are coming from. If you're wondering why the heck it becomes addition and subtraction, that's kind of how you prove that these are true. But don't worry about that. If you're just curious, that's kind of where it comes from, kind of. The one that's really the workhorse of what we're going to be using is this one, which is the natural log of a to a power. We bring the power outside of the log. That one we're going to use a ton. And then some other ones that are, you can plug the first 2 into your calculator, but if you can remember them in your head, they can save you a little bit of time. Whoops. We already saw the natural log of 1 is 0. The natural log of e, so what is the power of e to get e? You just need one of them. So the natural log of e is 1. If you have an e to the x inside of a log, so the natural log of e to the x, it's just going to be that x value. And also if you raise e to the natural log of x, it's also just that x value. E and the natural log are essentially inverse operations of each other. Like addition undoes subtraction. The natural log undoes, quote unquote. Exponentiation is what the big word is for E. So if you ever have that, it's just reducing to that x value. So we'll use these a little bit, and we won't be able to get to solving logs. That will have to wait, and we won't get to that. But we got through a decent amount, so it's good. So evaluate the following without using a calculator. So if we have e to the natural log of 17, again, those are kind of inverse functions of each other. So since we're raising e to the natural log, they kind of cancel each other out in a way, and we're just going to get 17. We have natural log of e cubed. Again, the natural log and the e kind of cancel each other out in a way, and we're just left with the e. Also, think about the relationship. When it's written like this, think about that relationship. This is saying, what power do I have to put on an e to get e cubed? I have to put a 3 on it. Like to get e to the third, I need to put a 3 in the exponent. Anyway, this other one takes a tiny bit of an extra step. So, and this kind of relationship between here and here is going to be very important to us in the next chapter. If you aren't aware, two things, I'll do it in 2 steps. The square root is equivalent to a 1/2 power. And then if you have a exponent in a denominator, you can essentially bring it up to a numerator, but it becomes a negative power. So 1 over the square root of e is equal to e to the negative 1/2. So then if we use the natural log in e and we essentially cancel them out, we'll just be left with the negative 1/2. Questions on those? Okay. We've got 2 more problems that have 1 or 2 parts to them each. So rewrite the following as a sum or difference using simple logarithms. So essentially these are using those properties. We're going to use these first 2, well, and the last one. We're going to use these 3 to rewrite these. So what you want to do first is notice that these have multiplication in the top and the bottom, but ultimately kind of it's ultimately a fraction, right? It's ultimately the 3x squared divided by yz. So the first rule we'd want to use is we'd want to use that kind of what am I thinking? Division rule, if you will, to turn it into this. The natural log of the numerator minus the natural log of the denominator. And once we do that first, now we can use the multiplication rules to split them up further. So in the first one, the natural log of 3x squared, well, that's the natural log of 3 times x squared. So we're going to break that up into the natural log of 3 plus the natural log of x squared. Now, we need to be careful in the back. We need to add a set of brackets. Well, there's another option, but I'll talk about that in a second. Because if we break this up, it will become the natural log of y plus the natural log of z. Right? Just using that multiplication rule on that, natural log of yz. If you didn't have the brackets there, what that would imply, so if the brackets weren't here, this is technically now the only thing attached to that subtraction, which if you were to then try to squish it back together, if you did it properly as it's written, only the y would end up in the denominator, which is not what we started with. So either we need to tack on a set of brackets, which I think is the easier way, or if you wanted to, let me write it in maybe blue. The other option would to just be to make the other one negative as well. You still split it up, but that one has to have a negative on it because it was in the denominator to begin with. Or just think of it as the fact that you would have to distribute that negative, if that makes it easier. Whoops, whoops, whoops. I personally would say just put it in brackets. I think that's the easiest one to wrap your head around and to make sure you're not messing it up. There's one last thing we can do to this. So the natural log of 3 is just the natural log of 3. But we have a natural log of x squared, so we can pull that 2 out. So whenever we have a power, and I'm just going to keep these in brackets for my answer, just because I feel like it today. Other days I probably would distribute the negative, but today I'm just feeling like leaving it in brackets. And now there's nothing else we can do. There's no more multiplication inside a log. There's no more division inside a log. There's no more powers inside the log, so we're done. On your homework, essentially how it sets it up is it writes out, you know, the natural log pieces. It wouldn't have something like that on there. And then essentially asks you to fill out the constant in the front. So just be aware of that when you're looking at your homework. And it's actually to try to help you out, because trying to ask you to write the entire thing would probably be a disaster of notation. So this second one, again, is technically, you know, my brain stopped working. A division. It's ultimately a division. There's multiplication in the numerator and denominator, but the first thing we need to deal with is essentially breaking up that division using our rule, which tells us that we break it up using, nope, that's a cube. Subtraction of 2 logs. Now I'm going to focus on one part at a time. So let me focus on that natural log a squared b first. So the first thing we would need to do here is to break up that multiplication into natural log of a squared plus natural log of b. And we're going to leave the back for now. We'll deal with that in a second. And then to save myself space, the next one I'm going to go is this direction. And then the last thing I can do on those front two is the natural log of b is just going to stay, but I can bring that 2 on that natural log of a squared out front. So now I need to deal with that back piece. Now be careful. I know that there's a c times d in there, so you might think that you need to use the multiplication, but we actually need to use the power one first. Because notice that the power of 3 is on the entire thing of CD. So the first thing, so now we're good on the front. But we need to bring the 3 out. Whoops. First. And now we can use our kind of multiplication addition rule, if you will. Now we also need to be careful here, because we'd also want brackets, or we would have to be careful to distribute. We would have to be careful to not only distribute the negative, but also the 3. Which is why I think brackets is just the easier thing. Just tack it in brackets if you've ever got to do something. If it's ever behind a negative, slap it in brackets. Or parentheses. I just like using brackets because there's already parentheses floating around. And then we'd be done. I was hoping to get to the other direction, but we didn't, which is okay. I might have us do this last bit on Monday just to go the opposite direction, just so I can squeeze it on the exam before we go into a completely different process. So I'll probably have us do that first thing Monday. It's just the same process, just backwards. Instead of writing it out fully, we're just gonna compress it together. So if you need to leave because you have a class, leave, or you just want to leave. I'm going to say some things really super duper quick before I end. So Monday, we're going to do that last question that I just mentioned. And then for the rest of the class, we'll be reviewing. So if you have specific things that you would like to go over, any specific topic, or you find a specific question that you want me to go over, we can do those first. And then I'll try to also have some stuff planned out in case no one has questions. So we'll do a review on Monday, your exam's on Wednesday, lecture on Friday. Your review will be up later tonight. The answers will be up by the end of the weekend, hopefully on Saturday. Homework can be pushed back till the 15th. I will be putting that out on an announcement later. I think that's it. If you have any questions, feel free to stick around. Otherwise, have a great weekend. I will see you on Monday. Yeah.